Please title these notes Integrals 7 Notes, Strange Integrals, and write today's date. By the end of this lesson, you should be able to use the first fundamental theorem of calculus in non-straightforward ways. So one of the things that's really important for these problems is that you must be able to translate between the different forms of the first fundamental theorem. First, you have to be able to identify that one function, it can be a number of different ways that it can be written, that it's the antiderivative of another function. And this can be told you in several different ways. One, it can just be directly stated. Capital F of x is the antiderivative of lowercase f of x. But it can also be told to us in another way. We can be told that one function is the derivative of another, which implies that one function is the antiderivative of another. So we could also be told that the derivative of capital F is f of x, which means if one function is the derivative of another, that means the first function is the antiderivative of the second. We could also be told we have f and f prime, which means f is the antiderivative of f prime, and so on and so forth. Anytime that we're told that something is the derivative of something else, we can also state it backwards, that something is the antiderivative of its derivative. If we know that capital F of x is the antiderivative of lowercase f of x, then we have to be familiar with all the variations on the first fundamental theorem. So we know the integral from a to b of lowercase f of x dx equals capital F of b minus capital F of a. But we can also go the other way. If we're told that we want to find f of b minus f of a, those are capitalized, that's the same thing as doing the integral from a to b of its derivative. We also need to remember that this can be thought of as the change in capital F of x from a to b. So if we're asked about that, or if we know that, that's what it's talking about. And we have to remember that this can also be thought of as the area under the f of x curve from a to b. So we have to keep those things in mind when we're working with problems like the following. So the function g of x and its derivative g prime of x are continuous on the interval from 2 to 6 and have the values given in the table below. What is the value of the integral from 2 to 6 of g prime of x dx? So the first thing that we're going to do is we're going to write the relationship. We know that g of x is the antiderivative of g prime. And once we clarify that, we can write the fundamental theorem. So right here, the integral from 2 to 6 of g prime of x dx is going to be the antiderivative of 6 minus the antiderivative of 2. So once we have that, g of 6 we know right here. It's in the table. It's 1. G of 2 is right here. It's 3. Voila. The problem is not a difficult one. The tricky part is figuring out, this tells you that one function is the antiderivative of another. That means you can use the first fundamental theorem and just do some substitution. The tricky part is realizing that you actually have the tools, even though it's not straightforward. We'll also see other problems like this one. Okay, so we're told that lowercase f is just this little semicircle from 3 to 5. That's the entire thing. And we're trying to find the value of uppercase f of 5 minus uppercase f of 3. We're also told that the derivative of uppercase f is lowercase f. So this is where we want to state what we know about the relationship. So that means we know that capital F is the antiderivative of lowercase f. So once I know that, I'm going to just state the first fundamental theorem of calculus, where numbers we're dealing with are 3 and 5. So the integral from 3 to 5 of lowercase f of x dx is uppercase f of 5 minus uppercase f of 3. And this is really useful because this is what I'm trying to find. It's this value right here. So if I can figure out what this is, then I'm done. The question is, how do I figure out the integral from 3 to 5? Well, one of my interpretations for the definite integral is the area under the curve, specifically under the f of lowercase f of x from 3 to 5. And because I'm told this is a semicircle, I can see it's a semicircle of radius 1. So I can find the area of a semicircle with radius 1, and that's this area under the curve. And there we are. So really what it is just putting together the different pieces that you know about this first fundamental theorem in sometimes creative ways. Sometimes we're going to be given more complicated versions of these problems. So the graph of lowercase g of x is shown at right. One, two, three, four, 5, 6, 7. 1, 2, 3, 4, 5. Again, that's just a flat line here. Then when we get to 2, it's got this weirdo funky shape until we get to 4, at which point it's a flat line again until 6. Very strange function. We're told that the derivative of capital G is lowercase g, and we want to find g of 6 minus g of 0. So the first thing to think about whenever we see this pattern is that if the derivative of capital G is lowercase g, then the antiderivative of g of x, lowercase, is capital G of x. That means we can write the fundamental theorem. 0 and 6 are the numbers we're dealing with. This is what we want to find right here. So we just have to figure out how to find the area under lowercase g of x from 0 to 6. Oh, I forgot to put a piece in here. If the integral from 2 to 4 of g of x dx equals 2.7. So now finding this area, when we look up here, we can find some pieces of it fairly easily. There's one little rectangle right here. There's one little rectangle right here. And so this has a base of 2 and a height of 4, so that's 8. Base of 2, height of 2, so that area is 4. But this part over here, really weird shape. We don't know how to find it. So let's just think about splitting this up into a whole bunch of different little integrals. So the area under g of x from 0 to 6 is the area from 0 to 2 plus the area from 2 to 4 plus the area from 4 to 6. Now, like I just said, two of these areas we found pretty easily. We know this one is 8, the area from 0 to 2. We know this one is 4, the area from 4 to 6, but we have trouble finding this area. Fortunately for us, if we look back at what we're given in the problem, we're given that this integral, the area under the curve from 2 to 4, is 2.7. So if we just write 2.7 in there, we add them up and we get 14.7. Sometimes we're not dealing with graphs at all. We're just dealing with writing an expression. So let's say we have this situation. If capital F of x is the antiderivative of lowercase f of x, and capital F of 2 equals 7, first thing we want us to do is write an expression for capital F of 6 in terms of lowercase f of x. So, first this looks like really kind of confusing and weird. But what we know is we know that we have this relationship, so it's already written out for us. So that means we can write the fundamental theorem. We've got a 2, we've got a 6 in our capital F's, so let's go from 2 to 6. What we're solving for is this capital F of 6, write an expression for capital F of 6. So to get it by itself, we just have to add whatever f of 2 is to both sides. So it should be dx. And we're told that capital F of 2 is 7. And there we go. Another way to think about this is what we did in earlier units, where we said, okay, if we know the value of y when x is 2 for this capital F, we start with that value, and then we add the change from 2 to 6 to get our capital F of 6. And we know that another way to say the change from 2 to 6 is to say the integral from 2 to 6 of f of x. So it's the same thing we were doing a couple units back, it's just that now we're writing it with this new notation. So we can do the very similar thing if we're told to write an expression for f of negative 2 in terms of f of x. And the way that we did this before is we said, okay, we're going to start with the smaller one, so we know f of negative 2, and if we add to that the change from negative 2 to 2, and the integral of the derivative is the change in the function, then that's going to give us f of 2, which we know. F of 2 is 7. I can subtract this from both sides. And that's going to give us f of negative 2. Alternatively, we could also have done it exactly the same way that we did up here, in terms of saying whatever it is that we started with, f of 2, which we know, plus the change from what we know to what we want to know, remember, changing these bounds makes the area the opposite of what it was. So negative integral from negative 2 to 2 is the same as the positive integral from 2 to negative 2. So f of 2 we knew was 7. Like that. The final type of problem you should be able to handle are problems that have constants for bounds. So those are problems like this. If the integral from a to b of f of x dx equals 3a plus 2b, find the integral from a to b of 2f of x plus 3 dx. As we've done before, we're just going to break this apart. So the 2 is along for the ride. Now notice that we've been told what this is. Integral from a to b of f of x dx equals 3a plus 2b. So we can just take that out and replace it. This one, we can do our antiderivative like normal. It's from a to b. We're just going to treat a and b like they were any other number. So that's 6a plus 4b plus, got 3b minus 3a. And now I can just combine like terms. 6a minus 3a is 3a. 4b plus 3b, 7b. Let's do a check for understanding problem. If the integral from e to d of g of x dx equals 3e minus 4d, find the integral from e to d of 3g of x minus 1 with respect to x. Go ahead, pause the video, try that one on your own, and then restart the video when you're ready. So we can split this apart. The 3 is along for the ride. Now we know what this derivative or integral from e to d of g of x dx is. We're told right there. So we can just substitute that in. This one we know how to take the antiderivative from e to d. Distribute. As always, we're going top first, then bottom. So now we have 9 e's minus a negative e, so that's plus 1e, or 10e, and then 12d minus 1d. That'll give us negative 13d. And there we go. This concludes these notes.